Good morning, everyone. I am Joao Martino from University of São Paulo, Brazil. It's a pleasure for me to be here to present the 2020 IEEE Electron Device Society Sul Brasil Chapter webinar on micro and nano device. This event will take place between 13 and 29 of October. We start last Tuesday, and now is the second lecture. Today is the second lecture. The organization is IEEE Electron Device Society Sul Brasil Chapter. This is the webinar 2020 program. We start on Tuesday with core class lectures. I hope you had the opportunity to see. Now, today is the presentation of Professor Durga Misra with the talk entitled Dielectric Science on Today's Device. Next week, we'll have in 22 October a Delmo Tiscon presentation with the title Electrical Characterization from Micro to Nano Era. And finally, the other week, we have a Dr. Bertrand Pervet from IMEC Belgium with the title Advanced Transistor for High Frequency Applications. Every presentation will always take place at 11 a.m. Well, we had a link for free registration, mainly for the people who need the participation certificate. And also, if you do that, the registration is easy for us, that we can send you a reminder about each presentation. And all presentation, you have to push the YouTube link. And it's easy for you to select the day presentation. Today, we have a very great lecture from Professor Durga Misra from New Jersey Institute of Technology with the title Dielectric Science on Today's Device. The presentation takes place around 50 minutes, then we have more 10 minutes for questions and answers. Professor Durga Misra is a professor in the Department of Electrical and Computer Engineering of New Jersey Institute of Technology, Newark, USA. His current research interests are the areas of nanoelectronics, optoelectronics, device, and circuits, especially in the area of nanometer CMOS gate stacks and device reliability. He is fellow of IEEE and fellow of Electrochemical Society. He received the Thomas Collin Award from Dielectric Science and Technologies Division of ACS and the winner of Electronic and Photonic Division Award from ACS, Electrochemical Society. He edited and co-edited more than 45 books and conference proceedings in his field of research. He has published more than 200 technical articles in peer-reviewed journals and international conferences, including 95 invited talks. Then, thank you, Professor Durga, to accept to be here, to make your presentation. It's a pleasure for us to receive you here. Thank you, Professor.
I am just sharing my screen, and thank you very much for inviting me. And I hope everything okay now. So what actually I intend to do is today talk about a little bit dielectric science, what has been evolved. So first I talk about our university, NJIT, and it is right now the top tier university within the top 100 university of United States. I think I have some collaborators with Tokyo Electronics Center in Albany and Global Foundries Malta, and I have several graduate students who work on this project. So what I will talk about this outline of my talk is I will talk about a little bit of historical perspective, starting from 1800, and then we'll talk about silicon dioxide and the evolution to high K gate dielectric. And then the gate stack design with what are the things, the challenges and all with the high K dielectrics. We'll show some examples of gate stack design and look at some of the new applications or new approaches is doing, how the devices for artificial intelligence is cooking up, and also ferroelectric devices, and then summarize the talk. So in historical perspectives, how the dielectric word came through, actually Michael Faraday did it around 1800. The word dielectric to indicate that something analogous to electric current flow or something going on. That's why he said it's dielectric, actually in the capacitor. So it is because there is some sort of polarization takes place in the dielectric. That's why he started this word. And if you look at dielectric, has been tremendous contribution in technology and science in the sense understanding of the dielectric. It has physics, material science, chemistry, and in technology you can have reliability, performance, processing, manufacturing, characterization, modeling, many applications. But the biggest thing actually is let me go to this laser pointer. So this thing is because the transistor that has come up, the interface of dielectric to semiconductor and dielectric to metal has been a big challenge now. So we will talk about those things. So if you look at the electronic device evolution, you saw this last talk also. It started with a junction transistor in 1947. And then they also demonstrated in a different way the planar junction transistor in 1950. And then first MOSFET patent was filed in 1959 by Bell Labs. The MOS is metal oxide semiconductor device. And that actually revolutionized, actually so far we have seen the MOS transistor is still going in a big full swing. And then the first P-channel MOSFET was introduced by Fairchild in 1960, and the circuit, with RCA Lab, which is in New Jersey, he started the 16 MOSFET IC in 60. So they are sort of, the RCA Lab still gets the credit for MOS revolution. So the silicon dioxide, which was used as the dielectric that time for the MOS transistor, is a tetrahedral arrangement with one silicon bonded to 4 oxygen atoms, and it's an amorphous film. And it is being oxidized. That means it is grown, thermally grown, because oxygen reacts with silicon, on the top of the wafer to create the oxide. And that time there are many, the first transistor was in germanium, and germanium was also being tried for MOSFET, but it was not successful because germanium oxide was not the best oxide to work with, and it was soluble. I will talk about that later on. And then the silicon MOSFET became the norm because of silicon dioxide. So if you look at the exploration of silicon dioxide, as I mentioned, the electron flows just below the silicon dioxide in the MOSFET. So the interface is very critical to understand the interface. I will talk about a little bit on that. So the exploration started 65 years ago because of some instabilities they were observed in the MOS device. There are several listed during that time. One is the alkali ions, surface ions, polar molecules inside protons, oxide traps and oxygen vacancies and heterostructure models. So those sort of things are going on. People who are looking at the blind men exploring the big elephant and talking about what is actually happening. So this was a funny article came out in 1974, and then also it's reproduced several times. These are some of these. If you can see, there are surface ions, alkali ions, the sodium ions were there, and those things all sorted out. So, but still, we are still looking at some of those issues even today. So what is this interface that is such a big deal? If you look at silicon, MOS transistor was mostly in 100 plane. That is because of the crystal plane, because of the number of defects at this, or number of bonds available is less compared to silicon 111. But what people found out, there is, even if you form a very nice oxide, there are some unpassivated bonds that was there. They are called the PB centers. And in silicon 100 plane, they have two different ones. One is PB0 center and there is a PB1 center because of the complexity there. That is actually because of the unpassivated bonds and the orientation of the oxide, initial oxide that forms. And that was, you can calculate the interface defects density, and through as a band gap energy, there is a distribution of those things. You can see for 1001 is there. But there is a solution to that. Actually, the typical passivation, these, the exposed bonds, which were actually creating a lot of trouble with the electron mobility and hole mobility in the channel, that was resolved by this passivation with low temperature forming gas and hydrogen anil, because hydrogen can passivate those bonds. So this was solved, but the other problem is to find out these defects, find out the problems in the dielectric. The MOS capacitor was studied extensively, and we have, you know, there are two dielectrics, two capacitors there. One is the dielectric capacitance, and also there is a depletion capacitance there in series. So the characteristics of the MOS capacitor is like when the ideal MOS capacitor, this goes down in high frequency application, and low frequency it goes up because the depletion layer is sort of invalid at the low frequency. But if you have without defects, you can see there is a flat band voltage. Flat band voltage comes because of the gate metal or polycrystalline silicon, and also the defects of the oxide charge. And then if you have defects in the oxides, this curve shifts to the right, and you can see these defects. You can so estimate electrical active defects, how this can be, how much they are available in the capacitor. That has been studied many years ago. There are books written on that thing, huge books and many books written. The other thing also, when you stress this device, the dielectric degrades also, because when there is electron injection comes in through the gate towards the silicon, there is some hydrogen can release from those passivated bonds, and then create additional defects inside this, in the dielectric. As we can see here, the hydrogen goes up and creates defects also inside dielectric and also in the interface. So that creates a dielectric breakdown. Also the bias temperature instability, or BTI, which is NBTI for P-channel transistor and PBTI for N-channel transistors. And also because of the electron, high energy electrons at the interface, the knockoff of the hydrogen also does the hot carrier effects. So this has been well understood. So that is actually the initial part that I wanted to mention. But we cannot go without what is happening today's device is Moore's law. As you know that Moore's law has been changing. We are 5 nanometer transistors, what Apple recently declared for their Bionic 14 chip, that is the A14 chips, and that is one contributor. But this, we have not neglected our dielectric, so I'll go over this. So this is sort of the technology trends. It started in 90 nanometers to, if you look at as today, they're exploring the 3 nanometer transistor. And then the device also gone through the many transformations. The memory devices also gone through many different transformations. Lithography, also extreme UV lithography was there. And plus, there are a lot of new research and new devices that is happening on the, whether it is molecular size, 2D graphene, single electron transistors, and then AI devices, quantum devices. Those are all coming up now in the research phase. Some of them are already, to some extent, reality. And what we will see everywhere we have, the dielectric still plays a critical role. So here is some of the electron device evolution itself. The planar device became FinFET because of the scaling and the performance control. That's why this FinFET came up. And in the FinFET, you can have multiple fins. You can still see the dielectric still there around the fin in the gate. There's another type of changes also, because if you do SOI devices, that is actually coming up, because now global foundries and all those places, they are making a lot of SOI devices. They are very good for high frequency applications. And then we have nano air FET. Nano air FETs, as you saw the last Tuesday talk, there are a lot of nano air devices are coming up, both silicon and germanium devices. And then in the scaling process, if you look at the Intel devices, in 19 nanometer we have planar devices, 65 nanometer we have planar devices with a lot of stress in the substrate, so that improved the mobility. And then in 2007, the first time high-K dielectric was introduced, which I will talk about a little bit. But the high-K dielectric is actually deposited. It was not grown like silicon dioxide. High-K dielectric was deposited, and then that was a planar device in 2007. But when you went to 32 nanometer, also was planar device. But in 22 nanometer, Intel introduced first time the FinFETs, and also for 14 nanometer is all FinFETs. And in the process, the metal gates were introduced. Metal was used in the beginning in 60s. Aluminum was used as the metal gate of the MOS transistor. Then because of the processing complexity, aluminum melting point is low, so they moved to polycrystalline, heavily doped polycrystalline silicon gates. And that was continuing for a long time. And when we introduced high-K, it became then changed to metal gates again. So I'll talk about a little bit about that. Again, the gate stack for new generation, if you look at, these are some of the SEM pictures of FinFETs with multiple fins. And look at the interesting thing is that we saw the design, but there is a carving around in the fin. So that creates some of the issues. I will mention that. And then obviously there is that means it has a different planes all around. So it's not 100 plane or 111 plane. So this is also came up with the silicon nanowire devices. And this is most recently the prediction that we still have the dielectric, the high-K gate insulator still there. And there is a band engineered semiconductor that goes in there. And so obviously it is fully depleted, as we saw that thing in SOI devices. And low resistance source and drain, actually this is the new trend of the device. We will see those devices soon in the market, but they are still, integration has not been completed yet. So also in the DRAM technical issues, dielectric plays a huge role, and especially right now the high-K dielectric, they have cylindrical structures, they have pillar structures which are coming up now. And to have, again, the higher capacitance, if you do that, high-K dielectric, so that we can have a lot of capacitance there. The other thing also, which I will not cover that much, is the low-K dielectric, which is in the copper interconnects. We have the dielectric here is the mostly low-K dielectric. And there is a lot of research has been going on. People are thinking about coming down to 1 to 2 dielectric constant, that sort of devices with the number of metal interconnects that is being used today. But I will mostly focus on the high K dielectric. So what happened actually in when you have 180 nanometer technology, then went to 130 or 90 nanometer technology. That time the silicon dioxide will change to silicon oxynitride, because nitrogen has the capacity to block any dopant atom diffusion to silicon, but that actually was there. The other major problem when we came around 65 nanometer technology and slowly trying to go down, the leakage current, the dielectric thickness became 1.2 nanometers. Below 1.2 nanometer entered the tunneling region for this electron tunneling. So that actually started the high K dielectric research in around 2000. And then around 2007, the first in the 45 nanometer technology, they introduced the high K dielectric. It was deposited, so it was very challenging in the beginning, but it showed a very low leakage current, as you can see in this leakage current, and drove the EOT, the equivalent oxide thickness, towards points below 1 nanometer while limiting the leakage current. So then the first device, it was not easy to deposit high K dielectric directly on silicon. So there was an interfacial layer that was there, the silicon dioxide interfacial layer. But in the subsequent processes, actually that this oxygen from this area was scavenged out and then made the high K on silicon. So that became much better in terms of the interface is still was an issue, but that somehow resolved some of the issues there, and we can still have high mobility devices. Now, since we can deposit this oxide, then the idea came that we can introduce germanium or in gas devices, the indium gallium arsenide, to enhance the mobility. So I will talk about a little bit about the germanium and in gas, how the high K dielectric, what are the challenges there and how people have solved those problems later on. So this is actually the trend of dielectric in modern devices started with zero interface and sort of things. So the idea is when we started the higher K metal gate and this devices started, the high dielectric constant is just to go down the EOT to 0.5 nanometer, the equivalent silicon dioxide thickness sort of things by putting just the capacitance, keeping the same electrical performance. The idea of which material will go in, first of all, this should not have any reaction with silicon or germanium or 3,5, and it oxides with high heat for formation so that it can be deposited in low temperature. And then hafnium oxide became the leader, and then they are now actually hafnium zirconium oxide, hafnium lanthanum oxide. There is some sort of combination of oxides that are actually happening. And it has to be stable also at certain temperature, low diffusion, and amorphous was the original idea. Now I will show you some things are changing. And then the interface, which is also is a big issue. And then the wafer size from 300 millimeter to 450 nanometer wafers it should be uniform. But up to 300 millimeter, it was a fairly excellent quality of deposition. So there are several challenges in this, and the first one is the polysilicon gate that was there. Started with polysilicon gate and high K dielectric, but then they found out because of the phonon scattering, there was the electron in the channel was very turbulent because of the charge in the polysilicon gate and the limit number of charges. And then when they introduced the metal gate, it became much smoother. The electron transport became much smoother. The reason behind is in the large devices, the silicon depletion layer inside the silicon, even though it was very small, or less than 3 angstroms or 0.3 nanometers, it was still creating a lot of problems for the smaller devices. And that became a big issue. And now when you introduce the metal, and also, as you know, the polysilicon gate doping was very carefully monitored because to set the threshold voltage, because it contributes to metal to silicon work function difference. And also, obviously, the oxide charges will be there. But work function difference is a big issue. And how to select a metal that will be the, so this mid-gap metal that actually came up with titanium nitride. Many people are also modulating that metal to move the exact location of the metal work function. So that way the threshold voltage will be completely controlled and very well reproducible. So that's what actually the metal gates came in. So this relates to the dielectric again. Now, when you look at these devices with the high K dielectric, which is, once it is degrades, everything is a problem. So there are the major device challenges who are there. For example, in this device, if you look at it's a perfect device, but there are different crystal planes the gate will face, and the high K dielectric will be deposited also in different crystal plane. And in the edges also, they are not as sharp as we see here. There is some sort of, the corners are actually changes. And then we have breakdown, because the voltage, even the voltage scaling has been done, but there is still, there is a possibility of the, because of the corner rounding and all these things, it creates some of the issues in non-uniformity of dielectric around the corner. So that creates additional trouble of the dielectric breakdown. Again, the bias temperature instability, which is the BTI, which is creates, because when you are applying voltages, then suddenly the hydrogen release model, there are several models actually, the NBTI and PBTI, but that creates defects, and then the threshold voltage shifts over time when the device operates. So that is, but luckily for PBTI, for N-channel transistors, this is a little bit reduced for the FinFET devices. The hot carrier injection is also as an issue, and it's because there is some self-heating of the fin itself during the operation. That also exacerbates the hot carrier injection process. And that, and then because device is so small, we have soft error issues. That means in the past, one alpha particle cannot kill one transistor because transistor was so fairly big. Now, if one alpha particle can kill one transistor, so that actually is radiation level. So these are some of the issues now of the reliability. Then comes the processing challenge. How to do the deposition more effectively and uniformly around these fins is a big issue. So there is a new technology that came out, the deposition technology called the atomic layer deposition, or ALD. And that is changes smoothly compared to CVD and ALD. If you look at CVD, actually you have a precursor and you have oxidant, you have some inert gas that monitors this. There is a film growth that takes place smoothly here. But in ALD, you have you send the precursors in a cycles, and then you have oxidants also in a cycle, and then you have inert gas in cycle. So depending on the cycle 1, cycle 2, like this, you can deposit the dielectric on the top. There is that actually does the similar process as in the CVD, but it is deposited in the cyclic process. What advantage it has is the step coverage. Because normally if you do deposition by CVD, you will not be able to deposit uniformly on the top of this silicon, the film, and the uniform thickness, but the ALD actually improved to 100% step coverage. And I just showed you before, the memory devices, they are all cylindrical structure, so that is also very useful. And so the step coverage became much better in the deposition technique. And also because of the cyclic structure of this deposition process, and also the step coverage, there are a lot of new ideas came up. Here is one example of the multi-layered structure you can deposit, because you start with a silicon interfacial layer, and then you go for the 20-cycle hafnium oxide and then hafnium aluminum oxide. That way you can control, or you can go for a sandwich structure here like this, and that way you can control the amount of aluminum that you can actually introduce in hafnium oxide. It is by cycling, while the thickness can be still around 2 nanometer or 2.5 nanometer, but you can do this control, and then control the aluminum introduction inside hafnium oxide to 1 to 7%, which was very difficult in before, because either you do aluminum oxide or hafnium oxide, and now this ALD process actually can allow those. That's because the aluminum was introduced because of the temperature that you go through. The device goes through several temperatures before it's completed. The science behind that, if you add aluminum, the percentage, then the crystallization temperature. Once the hafnium oxide, which is amorphous, it crystallizes around 650 to 700 degrees Celsius. That way it will, most processes are very high temperature, around 900 to 1000 degrees. Sometimes you may have to go through the dopant activation process. And during that time, the high K dielectric can crystallize. So to avoid that, aluminum was introduced. But this is like the XRD, the gradual incident XRD process. You can see the aluminum can be controlled very nicely while you increase the crystallization temperature. Another thing also, when you introduce aluminum, the high dielectric constant of hafnium goes down a little bit. So that has to be optimized. We did some of the devices, looked at their leakage current and added some. So the idea is, if you add the, increase the concentration of aluminum, it reduces the crystallization temperature and then also reduces the interface state density. So that is, and also obviously leakage current. And if you look at the dielectric constant, that can go to, if you some of the devices we found it's extremely high dielectric constant, that because it forms a lot of crystalline metal. So you can go to orthorhombic structures, and from the tetragonal to cubic phase, and sort of different crystallization of hafnium oxide gives different dielectric constant. So if the crystallization is heavy, then dielectric constant goes up. But it doesn't really solve the problem of leakage current and also interfacial defect. So we have to optimize both. You can have some crystallization, but if you have a polycrystalline hafnium oxide, then it has large leakage current. So these are certain issues we looked at in the aluminum and hafnium oxide. Another thing I mentioned, that we can add zirconium into hafnium oxide. If you add zirconium by small percentage, for example, here is one example of 0% zirconium to 100% zirconium. If you add that one and look at the crystallinity of this film, actually this changes from monoclinic to, there is two different, this is full figure measurement as well as the GI XRD spectra. Actually, there is a tetragonal phase stabilization. Tetragonal phase is a tetragonal crystalline phase, but it results much higher high K value. So this is actually one good thing. But once we start this, the other thing I mentioned, because of the ALD processing, we can actually do several interesting things around it. Like, for example, if you deposit few cycles and then anneal the sample, and then deposit few more cycle. Even before you complete 3 nanometer of dielectric, you can have several deposition and anneal, deposition and anneal. That way you can densify the film and improve the characteristics of the dielectric. So also there is another process started, deposition and plasma exposure. What plasma exposure does, if you give very low energy electron exposure to the surface, it actually reduces the number of oxygen vacancies and increases the quality of the dielectric. And so that is called DSDS. We call deposition annealing as DADA and deposition and plasma exposure as DSDS. So many other treatments you can do during this time. For example, introducing, I'll show you some of those issues, introducing additional oxygen vacancies you can create and take away the vacancies. So reduce, and depending on the applications, people are trying to do all those different processes during the deposition of this 2 to 3 nanometer of dielectric. So in this case, if we look at this plasma source that I talked about, that we can do plasma exposure, it is done by slot plane antenna plasma source. That has been introduced in many of the equipment that in semiconductor industry is using. Only thing is, I can say this is we collaborate with TEL and the Tokyo Electronics company that was in Albany, New York, and they are using mostly slot plane plasma antenna. So this is actually a slot plane plasma that is created. This is extremely high density and low electron temperature, and then the wide range of process window. And this doesn't really form the plasma. There is a plasma generation region, and the wafer, there is a plasma diffuser. So it is not very high energy, or this doesn't create any damage. So this also shows how the distance from the window, actually this electron density goes down, but it is fairly very high at the wafer surface, but also electron temperature is quite low. So that actually gives us, because it's separated plasma generation and the process region, so then that's an extremely low damage plasma process compared to electron, cyclotron, resonance plasma, or inductively coupled plasma, which are heavily used for etching. This is actually for process control. So you thinking about this, we started with the idea of DADA that I mentioned. If you do simple PDA, as let's say you take as deposited film, whatever the leakage current you have, if you do a post-deposition annealing or PDA, then the leakage current goes down. And then if you do post-deposition annealing, deposition annealing, like a cyclic process, the leakage current goes down further. So you can make actually DADA or DSDS samples. You can create plain hafnium oxide or hafnium zirconium oxide with different zirconium percentage. That sort of things can be created in this. So we looked at some of those devices. It's because of the plasma exposure, the film become densified. So the film thickness, both the interfacial thickness, that is whatever we had this in these devices, we have an interfacial oxide. That device thickness went down compared to this is hafnium oxide, and this is hafnium zirconium oxide, 80% zirconium oxide. In all cases, when you expose the plasma, the densification of the film, both the dielectric thickness went down because higher densification, as well as the interfacial thickness also went down. These are actually physical measurement. Now, when you look at the CV, because of this, also the EOT, actually there is a significant improvement of EOT. That's because the dielectric constant, once the dielectric constant of the dielectric goes up, then EOT comes down for the same one. So you can see compared to hafnium oxide, hafnium zirconium oxide actually has a much better EOT that we found out. And then this is this is one way of the dielectric film quality. Then we got to look at the interface state density. What actually happens with the interface? So that also we showed, if you look at in the silicon band gap, mostly in this figure, you can see the the interface state density actually goes down for the DSDS sample with hafnium zirconium percentage. So both also 31% and 80%, 31% and 80%, both cases is went down. So this is along with the EOT, because once EOT goes down, and then we reduce the EOT, but same time we should make sure the DIT also goes down. But here actually we see that this is hafnium oxide still does a little bit better in terms of EOT as a DSDS process. So then we can look at DADA process and also DSDS process. Still, some of the cases we have that has to be optimized. So, but DSDS process is much lower, 1.56 to 10 to 11. So, whereas DADA is much higher. So, this is we discovered that, and then we reported to this, published this work. And the leakage current, and as I mentioned, the time-dependent dielectric breakdown. We saw the leakage current when the leakage current is lower, and then the breakdown voltage also, the time to breakdown is also quite high. So in this case, you can see this for DSDS sample with 80%, we have very large time to breakdown, because we estimated this is a 10 years breakdown, but this is just showing that the both charge to breakdown from the Weibull plot, you can figure it out, the charge to breakdown and leakage current, compared to the other devices. Even for the hafnium oxide, it was not that good, the DSDS hafnium oxide. So this is giving some idea of how this is happening. So I will go to now a little bit germanium devices. Germanium devices, because germanium has high mobility, and I mentioned before, because we are depositing high K dielectric, we can make a p-channel germanium FET, and also because of the large hole mobility, and then we can go 3,5 NFET for 3,5, but 3,5 interface of the high dielectric material or interface was a big problem. So people are now saying, why not we have both germanium PFET and germanium NFET, and that can give these things. Germanium is compatible to silicon technology, and it has a large potential for scaling. So we can actually do that, and then we can also do a strained substrate as well as high K metal gate. And it is also possible to make germanium. There are a lot of reports. IMEC has reported already germanium nano-air FETs. So high K germanium was, when you started, I will just quickly go through this. When we started this one, the interface also was a big mystery, and it was we try to passivate these things. And so surface passivation we can do by many people tried many different passivation. That is nitrogen passivation, sulfur passivation, and then post-deposition conditioning and sort of things. Because the native oxide, germanium oxide, is poor electrical properties, so that was the extremely unstable. And then we tried some of those things with IBM as well as with IMEC. And then the interesting part is it is different compared to silicon dioxide, the interfacial layer and this thing, because germanium system has no germanium dangling bonds at the energy gap of silicon. It is actually in the valence band, below the valence band. So this actually has some problems to detect the dangling bonds of germanium. And then we looked at when you do the nitrogen passivation, it showed the hysteresis went down, but it showed a lot of frequency dispersion. So the passivation was not a solution. So what can be done? So the key challenge is to have this improved interface quality. And then to do that, why not we try the actual germanium oxide to see if we can introduce that thing somehow, and then in a proper way so that we can reduce the interface quality. And then the plasma treatment can improve. So we should try, why not we try some plasma treatment in there. And then also aluminum, you can still use aluminum as a barrier layer or something to prevent the germanium diffusion into high K layer. So we did one experiment. What actually in this experiment we had this zirconium oxide, aluminum oxide, and this is actually a technique called the SPAO. So we did actually first we gave one clean the surface. We exposed to plasma oxidation. This is slot plane antenna plasma that I mentioned before. Oxidation, and then we did after aluminum deposition, we did also the plasma oxidation, and then after aluminum oxide and zirconium oxide was deposited, we exposed to also the slot plane plasma antenna. So that showed much better. Once we have this in between this case, actually it is improved the increase the depletion capacitance, that means improve the EOT values. And then so that gave some idea that now let's look at the device, why this improvement took place. That is to understand. Also we looked at the interface density also came down, and it was the best also for the one which is in the middle. Then we looked at the crystallinity of this film, that what happens to the crystallinity in there. So if you look at in the XRD, we found all these films were still amorphous, so we have nothing to worry. Then we look at the XPS characterization to look at what exactly going on. Then we found out that there is a germanium oxide is being formed. And then the three different cases, if you look at the germanium oxide before the high K deposition was not of high quality, whereas the germanium oxide after the high K deposition came out to be pretty good quality. And this is the reason because of the SPA that we got. It creates actually a suboxide, not a stable, a stable suboxide, not a germanium oxide completely. And that actually helped to bring down the interface state density and also high quality and EOT. So those are the things. Then the reason, because that we found out that if we do first of all before the dielectric deposition, there is a unstable and fragmented germanium oxide. But when you do that in between or after, we found out this is a stable thin germanium oxide layer, and that improved the characteristics. So another issue also, we did some of these germanium gate stack. We looked at as a function of different percentage of zirconium, and then looked at the CV characteristics and accumulation capacitance and increase with germanium percentage. So we can see that the EOT will go down. But one interesting result we found, the CV hysteresis. CV hysteresis went up for a particular percentage. And if you look at the hysteresis, quite high, up to 50% of zirconium. So this is, even though there is a reduced hysteresis for 75% and 100%, but this is actually behavior we didn't understand. Then we looked at the IB characteristics. When you sweep the IB characteristics, typical devices, leakage current is such, when you sweep, the minima should be the exactly same location. We didn't understand that. So we thought, okay, what is happening? Why there is a positive sweep and negative sweep? There is a variation of this minima. Then turned out to be why this minima changes. That is actually the first question we asked. This was a few years ago. And then I discussed that thing with people in the research community. It turned out to be, this is very interesting result we found. That is the ferroelectricity in hafnium oxide. When you add zirconium, around 50% of zirconium, the ferroelectric properties develops. There is a polarization takes place, and then the origin is attributed to the orthorhombic phase. It changes to the orthorhombic phase. There is non-centrosymmetric orthorhombic phase. And these are actually being considered for the both random access memory devices as well as for the FETs. So this is the ferroelectric films, if you look at, this is the center symmetric. There is one in case of the perovskites, they are center symmetric and they are not ferroelectric. But when you have non-center symmetric films, they are actually the crystallinity they are ferroelectric because there is an energy shift. And then if you do the polarization plot, you can see how the electron changes, and because of the polarization, then it shifts from one direction to another direction. And that led to, this is the basics of the ferroelectric properties. There are a lot of modeling and understanding still going on. And then if you look at the crystallization, this XRD characteristics, you can see the XRD from the monoclinic. If you have a certain percentage of hafnium, zirconium oxide, there is a monoclinic phase. It goes from orthorhombic phase, which is this one, has the highest polarization. So this is actually the 50% of zirconium in hafnium oxide. And that gave the best result. That's why we saw these funny and interesting results of our IB characteristics. And it was just ferroelectric time. So there's a ferroelectric films were in hafnium zirconium oxide was around, sort of people who are predicting that it has a ferroelectric properties. Now we have hafnium oxide also has ferroelectric properties. So this was the started. And that led to many new devices now, because just the dielectric gave these fantastic results. That's why we are looking at many different devices. FERAM and also sorry, I will go back. So this is actually the ferroelectric devices also led to negative capacitance devices. Obviously, there is a ferroelectric tunnel junction FET, and so this is actually what started now. So you will see these things slowly will be integrated into the silicon CMOS technology. Another topic is being discussed now, the artificial intelligence hardware. What is happening there? What are the devices? Everybody is trying to talk about artificial intelligence hardware using memory cells and in-memory computing. All sort of things are happening. The basic device for that, this is the GPU, the graphic processing unit is now done, and also FPGAs were done. The main other things that I would like to discuss is neuromorphic computing, where this new brain-like architecture and device development is being accelerated to optimize the AI applications. And there integrates memory and logic together. So that's what people are working on. Here is some example. If you look at the human brain, the power consumption is 10 to 20 watt only, and does a lot of parallelism, report nets, and also ultra high density, plasticity. So there are a lot of advantages. But the most sophisticated supercomputers, if you use those, you can have this cat cortex has this many neurons. But using these computers, human brain can use 100 megawatts of power, equivalent to the current computation, that is the Van Neumann architecture if we're using. So everybody is now seriously looking at how to reduce the power in our systems. So that comes out. This is an example of artificial neural network. It's a simple model. What it does actually, it gets some of the synapses. When your action comes in, the synapses decide a synaptic weights that comes on. So here actually a crossbar array with all the synapses here, and they have different weights. So based on the input voltage and the conductance of these weights, which are different, and that way we can get a different current. And that's what actually the basic matrix multiplication. And these weights are sort of called the memory. And then because it will be multiplied in the same way, so this is called the in-memory computing. And the first device, this is the neuromorphic computing. In a sense, what is the process of this crossbar array switches behaves like a neuron. It is similar to RRAM devices or RERAM resistive switching devices. When you apply a voltage in the dielectric, there are a lot of oxygen vacancies are there. So they lined up, either formed in a soft breakdown mode or form a conducting filament. that reduces the temperature. Reduces the resistance. Once the resistance reduces, so you put the reverse voltage to this device, so that the conducting filament ruptures, and then it enters the high resistance mode. And by adjusting these the current and voltage characteristics, you can actually modulate the resistance or indirectly the conductance of this film. That way you can introduce different weights in different cases by adjusting different pulses. But the basic idea is how to start this gate stack evolution here. We did one example here is we created one gate stack. It's a metal to metal to MIM capacitor, which has aluminum oxide and hafnium oxide and different stack of metals. And then we applied the voltages because of the forming voltage. It was starting around 1.2 volts. It's reduced voltage, but the devices switches around 10 microamps. So 10 microamp is a very large current for the switching of these things, and we have 100 cycles. This is just to check whether the device is surviving 100 cycles or not. They all survived 100 cycles and they worked very nicely. And also, if you do change the compliance current, so 10 microamps, 11, 12, then you can set different. So this is actually called the multi-level storage, or you can have multi-level, weightage in there. So by adjusting this current level or the pulses, voltage pulses, you can have change the weight of or change the conductance depending on whatever is required for the multiplication process. But interesting thing is we switched this aluminum oxide from the bottom layer to the top layer. So this is actually goes to the top here, and then suddenly the switching characteristics changed. We went to 50 nanoamps of switching characteristics, and that was actually very amazing. 50 nanoamp from 10 microamp to 50 nanoamp, it is very low, and this device also survived 100 cycles that we are doing. So we are still working on this to solve this multi-level conductance process or resistance values. This is the low resistance, this is the high resistance case. So we are looking at those things and see what, okay, first of all, the science behind that, why it happens, why this power reduction. The activation energy of the oxygen vacancy generated in dielectric as a function of the applied field. That's why we have to look at how these oxygen vacancies line up to form this filament. And then if you look at the hafnium oxide is 4.3 electron volt. And then there is the aluminum oxide is 1.8 electron volt. So that actually is, that means the aluminum oxide creates a lot more, it's much faster compared to hafnium oxide, the oxygen vacancy generation. And then aluminum oxide layer also found is a high dielectric field because it has a low dielectric constant. If you apply a voltage, there is a large field drop across the low dielectric material compared to the high dielectric material. So that also enhances the oxygen vacancy formation. Also, we looked at the TEM characteristics of this aluminum diffusion. We saw the aluminum diffusion taking place. But the interesting thing is when you have the conducting filament and we have large number of oxygen vacancies at the lower part, then it doesn't form because most the ruptures and filament formation is taking place on the upper part of these things near the top electrode. So that's why it was not showing, even though you have large oxygen vacancy formation here. But when we switch the film to the buffer layer, the aluminum oxide buffer layer to the top conductor, then we found out that this is the power requirement for switching operation reduced significantly. So these are some of the research and understand. There is no modeling right now. People are understanding this again because you cannot see an oxygen vacancy inside the dielectric. No devices are available now, but we can always calculate those things and see. So the higher concentration of oxygen vacancies near the top electrode reduces the switching power. So that's what we found. So in the closing remark, I can say the high dielectric will remain as long as we have electronic devices, or we can have a dielectric always there. And then we have role of interface of high dielectric and alternate substrate like germanium will dominate, and or germanium or 3,5 or gallium arsenide devices. And reliability challenges need to be resolved. When you want to ferroelectric devices, they are working fine, but what are their reliability? They have not been studied yet. These are all new, and new applications also there in AI. Hardware for AI also is coming up, but they are still have a lot of variabilities, and if we cannot guarantee that if we program for this weight that will go into the little synaptic device, it will not be the best, or we will not know exactly what it is. So that is what actually the research is coming along. A lot of modeling work required there, both ferroelectric devices and AI hardware. So this is what actually the science and the dielectric. So I will say this. Thank you very much for your attention. Maybe I will take some questions now.
Thank you very much, Professor Durga Misra. Thank you for the excellent talk. It was great. You had here many people asking questions in different ways, and I will start using the chat, right?
Okay. Yeah, you can just put some questions there.
Exactly. Let's start with the simple ones, right?
Okay.
The first one.
Yeah, do you think the hafnium-based dielectric is the most important gate dielectric nowadays? Yes. Hafnium-based dielectric means it's not completely hafnium oxide, but it has a lot of different things mixed with it. A lot of people are doing for high-end processes is hafnium lanthanum oxides and hafnium zirconium oxides. So they are actually being used, but it is all hafnium-based. And then how could they understand the spin-free dielectric and what characteristic processing condition would present anything that a high-K dielectric film to consider spin-free of the development? So I am not really familiar with the spin qubits that is being used for quantum mechanical devices, but the processing is coming up with integration of different, like for example, plasma as well as dielectric deposition ALD, that they are looking at how to control different type of behavior, how to increase the polarization, how to increase the film density on different properties. But I'm not really familiar exactly how they are introducing the spin qubits in high-K dielectric.
Okay, thank you. Next two questions.
Okay, could the displacement of the minimum current and hafnium zirconium oxide be related to charge trapping at the interface instead of ferroelectric conversion? Some other amorphous high-K film present this. Yes. We try to explain this in the charge trapping because that's what actually happening, because once you have the charge trapping. But if you do a sweep, very fast sweep, the charge detrapping also will take place. And because of charge detrapping, the current should be in the same region. Of course, if you have deep defects, then there is a shift possible. But that actually we eliminated in many of the devices, not all the devices, eliminated most of the devices, the charge trapping characteristics. Of course, charge trapping is a serious issue in high-K dielectrics, but that we understood that one. We have several, maybe 20, 30 publications already on the charge trapping and detrapping process for DC and AC stress level measurements. But thing is, charge trapping is a effect. But we explained initially there is a paper we published in the Solid State Science and Technology Journal, and that we explained this current shift, the minimum shift in terms of charge trapping. But what actually happened then immediately around that time when I said this is the behavior, the hysteresis, if you correlate with hysteresis and charge trapping, it didn't really work very well. That's why there is an understanding issue. And then they turn out to be, there is some ferroelectric characteristics is taking place in addition to charge trapping in our devices. They are not perfect. So that's what we have noticed. Thank you. Very good question. Very good question. We were puzzled at that time. We always know charge trapping, charge defects.
Excellent. Professor, I would like again to thank you for the presentation, for the excellent talk. I think it was very interesting for us to have a good idea, an overview about the new dielectrics, or what they are researching, what they are working on it. Let me see. There is another question here.
Okay.
From Walter Saucedo.
Neuromorphic computing, how many activation cycles support the system and what is the response time on this network? The activation cycles actually can support many activation cycles. For example, we are looking at least 10 different resistance values or the conductance values of these neuromorphic devices. Many of those people are trying many different devices. Our idea is we can use the hafnium oxide based gate stack. We are trying now by controlled introduction of oxygen vacancy in hafnium dioxide, which is still on the phase. We are doing some work. We found that we can reduce the switching current to 3 nanoamps. So that we're working on, but this is still a little bit, we have some NDA with the TEL technology people. It's not released yet, but we'll be publishing that once it is approved. We'll be publishing soon. It is coming out to be using different material, like ruthenium as the gate metal, the top metal, and we can reduce still those things. And the idea here also to go to several, like at least 10 to 15 resistive cycles, so you can do these activation cycles with process by changing the conductance. Right now, some people have demonstrated this work with copper ion introduction in silicon dioxide, but copper ion in silicon dioxide will be very difficult to integrate with standard CMOS technology. So that's why that was not gaining any momentum. But people are looking at how we can control and understand the oxygen vacancies in hafnium-based oxides, so that if we control that and understand these the resistance changes, that way we can go to multi-level activation states. So that is actually still in the research phase, even though RRAM and all sort of things already demonstrated 2-3 layers of storage, but not similar to the artificial intelligence hardware required. Okay,
thank you for your question, your answer. I think it's okay. It's time now, 10 minutes, and then I'd like to thank again for the presentation. I think you have next time. I hope you get opportunity to come to Brazil.
Yes, I'm always looking forward to go there.
For presentation, right? In on-site presentation, right?
Yes.
And then,
I hope I have some of these
opportunity.
Yes.
I hope to visit you also. And then one final question.
Okay.
Final question.
From the atomistic point of view, where do the dielectric constant comes from in a dielectric thin film? So this, depending on the bond structure of this dielectric, how the bond is formed, based on that it changes the dielectric constant. For example, if we look at oxygen and silicon dioxide and hafnium oxide is a transition metal oxide. So this is it forms a bond in a completely different way than in silicon dioxide. That's what it contributes to the dielectric constant. And also, what is the structure? You have to look at the structure of this also, because we have noticed that if you crystallize the hafnium oxide from amorphous to crystallization state, the dielectric constant changes. So this is all the orientation of the atoms that actually does the dielectric constant increase. Thank you for the fantastic questions. I hope there is just some idea about the science and technology of today's dialectics.
Thank you very much, Professor Durga. I hope to see you again soon here in Brazil, or perhaps United States, or perhaps like that way. But I hope presently is better, right?
Yeah.
Thank you, Professor. Yeah. Bye-bye. Thank you for everyone to stay with us till now. And next week you have another presentation. Bye-bye.
Okay. Thank you. Bye-bye now.
Bye, Professor.